Okay, good afternoon, everybody. So it's my pleasure to introduce the next talk by Silvestre from the University of Chicago, and it has to do with upper bound for the Boltzmann equation.
Thank you, Cyril. Yeah, the title now was a little bit longer, but so I'm very happy to be here. Thank you for the invitation. Happy to be celebrating birthday. I'm not been actually for a very long time, but of course I can't compete with the other people who know you before I was born, right? But I met the first time I met you was when I was in graduate school. When you were visiting us, that was the time that young presentation that were to visit before you had the
Reborn. Reborn, but in another place, right?
Yeah. But that's before you finally had the actual position.
Exactly. That's true.
Luis, is your microphone on?
I don't know, my yeah.
Let's see.
Yeah, now it's on. All right. So what I'm going to talk about today is, well, I guess the title is Upper Bounds for the Boltzmann equation in bounded domains. So it's going to be solutions of the Boltzmann equation that certain hydrodynamic quantities are bounded, and we're going to get C infinity bounds. And this is for bounded domains, but I'm going to start by telling you also the story of what we did without the boundary first. Some joint work with Cyril. I'm going to start by telling you that, and then I'm going to tell you what we did and what we're doing in bounded domains now. So let's start with what the Boltzmann equation is, for those who haven't seen it. So this is an equation that tells us the evolution of the density of particles in some gas. So we have a function S that represents this density with respect to their position and velocity. So basically it's telling us some continuous version of how many particles there are at each position, x, and velocity v, and how this density of particles is evolving in time, right? So the left-hand side of the equation is the transport part, so basically saying that every particle is moving in space with respect to their own velocity v. And then there is a right-hand side, which is accounts for the interaction between particles. And a priori, the Boltzmann collision operator is this complicated integral formula, right? So this is evaluated. It acts on the function as a function of v. So for every fixed t and x, you take f as a function of v, and the operator q acts on this function of velocity. And so evaluated at every value of v, this is the same v that goes here. So we're going to have a gain term that is accounting for particles that are colliding, and one of them is becoming a particle of velocity v. And there is a loss term that accounts for particles of velocity v that are colliding with another particle, and they're changing velocity, right? So every collision is the frequency of collisions of every type of collision from v star to v prime star is modeled by this kernel B that is saying how often you have each type of collisions. And there are different modeling choices for this kernel capital B. All right? So the most common collision kernels perhaps are the one that comes from models of hard spheres. That would be if you think that the particles microscopically are like perfect spheres that are bouncing against each other. And then there is these other kernels that come from models in which the particles repel each other by some power law potential. And those lead to this other type of kernels that are quite a bit different. The parameter S and gamma are in this range. They should be related to each other, depending on the physical model, but I'm never going to use the relationship between them. So I take them as any arbitrary number where gamma is greater than negative dimension and S is in between 0 and 1. So there is a big qualitative difference between the hard sphere model and this power law potential, that the kernel capital B is not integrable with respect to the angular velocity, the deviation angle in the second case. And so the operator still makes sense because we have a cancellation here between the gain term and the loss term that compensates the singularity of capital B. But that singularity will actually have a regularization effect in the equation, because it's like, think about like the fractional Laplacian or integro-differential operators that have a singularity at the origin. So that singularity produces some regularization effect. And so since we're concerned with regularity estimate for the for the solution of the Boltzmann equation for the regularization effect, then the singularity is sort of, we really want to have that type of singularity in the kernel. So it's going to apply for this type of collision kernels, also called the non-cutoff collision kernels. So let's see. So this is just a remark that is sort of good to keep in mind. That is that from the Boltzmann equation, one can recover the traditional equation from fluids. So if one makes the collision kernel stronger by this parameter 1 over epsilon and take epsilon going to 0, then the solution of the Boltzmann equation will converge to something that everywhere is like some rescaling and translation of the Gaussian function. So if we follow the mass density, which is the integral of f with respect to v, the velocity density and the temperature density, then these quantities should converge as epsilon go to 0 to a solution of the compressible Euler equation. Now, the compressible Euler equation develops singularities in finite time. The fact that a limit of the Boltzmann equation develops singularities in finite time doesn't necessarily imply that the Boltzmann equation will develop singularities in finite time, right? So that cannot really imply anything by this by this observation. But what should we believe? And it's not clear. Like, should we expect the Boltzmann equation to be well posed and stay smooth for all time, or should we expect it to develop singularities? So at some macroscopic level, something should resemble some sort of singularity. But then the compressible Euler equation has different type of singularities. There is a shock type singularity, which is a bunch of fluids coming this way, another one's coming this way, and they crash each other, and it produces some sort of discontinuity in the solution. Whereas while the density and the velocity stay bounded up to this continuity. We cannot see a shock type singularity, or we shouldn't see a shock type singularity in a kinetic equation, because a shock is basically you have two different velocities that want to coexist at a point. And a kinetic representation of a fluid completely allows for different velocities to coexist. So shocks are not going to be a singularity for the Boltzmann equation. But there is this other type of singularity, that is an implosion type singularity. So the implosion type singularity in compressible Euler is when the density is going to infinity at that point, because all the fluid is concentrated there. And for as far as I don't know any reason to rule out an implosion singularity for Boltzmann. It's not something that has been constructed, or I don't know. It's something I cannot rule out. That's as much as I can say. So we don't know if the Boltzmann equation will stay bounded as smooth for all time. And it seems like a very difficult problem if the answer was positive. So this is a big open problem, let's say. So what is what is it that we can do? So the result that took a while and several stages, and it's a joint result with Cyril, is that if we have a solution of the Boltzmann equation for these kernels that correspond to these power law potentials, and we know that the macroscopic quantities, the mass density, the energy density, and the entropy density satisfy pointwise bounds, then the solution has to be C infinity. So it's a conditional regularity result. In a way, what this is saying is that other than the implosion singularity, there shouldn't be any other singularity, right? We're also taking away vacuum, so we don't want to have vacuum. Vacuum is sort of a special, requires another discussion. But so basically, it's saying that if there was any singularity for the Boltzmann equation, it has to be visible macroscopically, right? Or that there is no singularity that in the Boltzmann equation that is from a purely kinetic nature, that is not something that you wouldn't see in a hydrodynamic equation. So that's the vague description of the theorem. This is the more precise description of the theorem. So we have the F solution of the Boltzmann equation. We take it periodic in X so that we don't have to deal with boundary conditions. And this is a range of parameters in which the results apply. These were the parameters for the collision kernels. There is gamma plus 2s is between 0 and 2. We assume that the mass density is bounded below and above. The energy density is bounded above, and the entropy density is bounded above. And then in some range of parameters, is when gamma is in this soft potential range, we want the initial data to have fast decay at infinity, which we wouldn't need for gamma positive. And then we get an a priori estimate on all the derivatives of the solution immediately as for positive time. So let me say that this range of parameters is not the full range of parameters of interest for the Boltzmann equation. So one would also want to know what happens when gamma plus 2s is negative. But that's there is some important step in the proof that fails, which is when you try to get the infinity bounds. So this is the theorem that we have with Cyril. Some of the consequences or the things that you can do with this. One way to think about it is you can think about it as a continuation criteria. If you start with an initial data that is smooth, maybe we can produce a smooth solution for a short period of time. And then what the theorem is saying is that the solution will cease to exist only if one of the hydrodynamic quantities blows up. Because otherwise we have uniform regularity estimates. So the only way the solution can become irregular at some capital time, at some time capital T, is if one of these conditions of one of the hydrodynamic quantities is not satisfied up to that time. Another consequence, well, there is this famous result by De Villiers and Villani that says that solutions to the Boltzmann equation in the non-cutoff case will converge to equilibrium, and that result was conditional to the solution being C infinity with some uniform estimates on all derivatives. But now, since we have a result that is also conditional but gives us uniform estimates for all the derivatives based on a weaker condition, in a way it makes their conversion to equilibrium result depend on fewer conditions, right? Another consequence is that one can use the conditional regularity to produce global solutions if the initial data is close to equilibrium. This is all sort of an incidental finding. I never meant to be studying solutions close to equilibrium, but in a way, if you combine the conditional regularity results with the convergence to equilibrium of De Villiers and Villani with any short-time well-posedness result, then you can deduce that if the initial data is sufficiently close to the Maxwellian, with respect to whatever norm the short-time well-posedness, with whatever norm is in the short-time well-posedness result, then you get a convergence to equilibrium for initial data sufficiently close to the Maxwellian. This is because if the solution is close to the Maxwellian, then the hydrodynamic assumptions are automatically true. And if the hydrodynamic assumptions are automatically true, the function stays uniformly smooth. So the convergence to equilibrium applies, so the solution can never go away from equilibrium, basically. It's a very simple way. It's a very simple consequence in a way. Unfortunately, there is not too many short-time well-posedness results in the literature. This is something I find frustrating. There is actually more results about global well-posedness when when initial data is close to equilibrium than short-time results for arbitrary initial data. I don't know. I think it's an anomaly in the mathematical community that nobody really wants to do short-time existence results. So anyway, this is another consequence of the results with Cyril. So this is sort of the roadmap to get to that result. It's a several-stage program. The first thing starts with L-infinity estimates. And this is the only step in which we actually use the gamma plus 2s is non-negative. So basically, if we have a solution to the Boltzmann equation, and we know that the mass, energy, and entropy are bounded above, and the mass density is bounded below, then depending on those quantities only, one can get an upper bound for the L infinity norm of the solution at positive time, right? Then the second step is an integro-differential kinetic version of the Hahn inequality of the Cauchy-Nash-Moser theorem, and that gives us local Helder estimates for solution of the Boltzmann equation. The third step is Schauder estimate to get higher regularity estimate. There is a pointwise decay estimate. This is something we did with Cyril and Clément Moureau that basically tell us that the solution of the Boltzmann equation is not only bounded above uniformly, but has certain decay for large velocities, because of faster than any algebraic rate. And then we have to do some precise analysis of the asymptotics for large velocities to get global bounds and iterate and get the C infinity estimates. So this is more or less the steps involved in the whole proof in the program, right? So I want to talk about bounded domains today, and I want to talk about the very first step, which is the L infinity estimates for the bounded domains. So in the bounded domains, we have different choices of boundary conditions. This is a bounded domain in space only, which is what physically makes sense, right? The velocities are still allowed to be whatever they want, but the space is confined to a container for the gas, right? And so what would be the boundary condition? There are different choices that make sense. So one possible choice is to have specular reflection. That is, if the particle is coming this way, it's going to bounce back with a reflected velocity, right? So that if I take any point x on the boundary, f of txv should be the same as f of tx rv, where r is the specular reflection of the velocity with respect to the normal derivative, normal direction to the boundary. So n is the unit normal to the boundary here. So basically saying that the particles are just bouncing on the boundary, right? This is specular reflection boundary condition. Another common boundary condition would be to prescribe the value of the inflow. So we say how exactly the value, we prescribe the value of f for any point x on the boundary whenever the velocity is coming inwards, right? It wouldn't be correct to prescribe the value of f for the velocities that are going outwards, because that's determined by the equation, determined by the transport equation, right? If you have a blob here that is moving in that direction, eventually hits the boundary, and it comes from the inside, so it has to be determined by the equation. So the boundary condition is only for the values of f at the points where the velocity is pointing inwards. Okay. And then there is actually quite a lot of other boundary conditions. There is a diffuse boundary that is popular for whatever physical application, but they are complicated, so I prefer not to explain them in detail, right? And so there's many weird boundary conditions that one can consider. Bounce back is completely unphysical. It's like a particle comes here and bounces exactly in the opposite direction. Yeah?
Is there an outer pressure equivalent?
A what?
An outer pressure problem where you specify a prescribed pressure, like a gas inside a piston? With a
I don't know. So I don't know if you can model that maybe with some combination of diffuse boundary condition. So the thing is that when you try to be physically relevant, then the boundary conditions are mathematically messy, right? So I prefer to stick to the nicer ones. The diffuse boundary condition is you have a prescribed equilibrium density that is given by the boundary condition, but is scaled by how much is coming outside. But then there is lots of other combinations that we can do, like taking some sort of average between the diffuse boundary condition or prescribed influx, and I don't know. So the point is that there's many boundary conditions that come from physical models. I typically prefer to pick the simplest mathematical one, right? So I want to perhaps this is our recent preprint with Zimeng Aoyang, and which is the upper bound under the same hydrodynamic hypothesis, but instead of looking at the periodic box like in our previous program with Cyril, here this is in a bounded domain with any of the reasonable physical boundary conditions. Now, this is only the upper bound, right? It's a bound in L infinity. So if I go backwards, it would be the very first step in the program, and only the first step. So let me make a little comment about why we sort of need to do it again. So this first step in the program is proved with a maximum principle type argument. That is, we have a barrier from above. I look at the first point where the solution would cross the barrier, and evaluating the equation at that one point gives me a contradiction. And that's the way this L infinity estimate is proved for the boundary, for the Boltzmann equation with periodic boundary conditions. If we try to do that argument in a bounded domain, then we have the problem that maybe our barrier crosses our solution on the boundary. And then perhaps one can do something for some boundary conditions, but then the analysis would be very specific for each boundary condition. And it's complicated. These barrier arguments for kinetic equations, to adapt the barrier, it's not so simple, right? So instead of that, we chose to do something completely different. So the proof of this theorem is we get the upper bound with a more variational approach. So instead of a maximum principle, we take the barrier, we look at the integral of the function above the barrier, and we try to show that that integral stays zero. So it's like the variational way that you could prove a maximum principle instead of the typical maximum principle of finding the first point where your function touches the barrier. And by doing that, once you have this variational approach, then the boundary condition is very easy to handle. So I'm going to try to show you the ideas of proving this theorem, but then the boundary plays a very minor role. Is you have a boundary term that's just going to be negative, right? So it's more like an excuse, if you want, to come up with a different proof of the L infinity estimate. I'm going to show you a proof of the L infinity estimate that is not the one we had before, that is more variational, and that it easily allows you to handle boundary conditions, okay? But anyway, I have to start from the very beginning. That is how we deal with the Boltzmann equation, and how we express it and work with it. So I'm going back to the expression for the Boltzmann collision kernel that was in the first slide, and I'm going to try to move terms around and put it in an expression that I find useful. Okay, so first thing I do is I'm going to add this mixed term where I have v prime star, the same as that one, and f of v. Right, and I'm doing this to take a common factor and split it. So because if I add and subtract that term, then we have a common factor in the first two terms and a common factor in the last two terms, that we can take them out. And now I want this thing to think about this product as some kernel that applies to the incremental quotient from v to v prime, right? So this is a kernel depending on the solution f itself, right? And it's like when you have a nonlinear equation that is like a linear equation, but the coefficients depend on the solution. This is an integro-differential diffusion, and the kernel of my diffusion depends on the solution f itself, right? Then we have the second term, which is like a reaction term. We have f of v times this thing that, if you do the arithmetic, it ends up being a convolution of f with some function little b. So this whole thing is, if you compute it, is a convolution of f with some function little b that depends on that kernel capital B. All right. So the Boltzmann collision operator has this integral diffusion part with some kernel depending on the solution, and this lower order term that is f multiplied times the convolution of f with something, right? So for the collision kernels that I mentioned in the second slide, this little b is going to be the v to the power gamma, right? So of course, when this is a lower order term, so when we study regularity estimates, typically it's less important than the diffusion operator. But when we do the L infinity estimate, it's actually the one term that we have to fight, because the first term will have a maximum principle, the second term does not. All right, so what is that kernel? So I told you that the kernel was this thing, but I want to write it as a function of v and v prime. V prime is one of these, I don't know, it's pre or post collisional velocities, and it's parameterized in terms of v star and direction. So to compute to write this thing as a kernel of v and v prime, you have to do some change of variables and get some formula that takes some effort. So I'm going to tell you what it is, basically. So if you have a point v and v prime, what you get from that kernel after the change of variables and computing what it is going to be the kernel of the fractional Laplacian at v and v prime multiplied times some factor that is going to be an integral on a plane that goes through v and is perpendicular to v prime. So it says all the w's that are perpendicular to v prime, I evaluate f at v plus w and multiply that times that weight, right? So the kernel, the diffusion kernel, is in a way comparable to the fractional Laplacian, but it has a factor up front. And that factor depends on v and v prime, right? So in some places, the factor may be large, some places the factor may be small. So it's an integro-differential operator that is in a way elliptic of order 2s, but the ellipticity constants aren't so easy to control, right? If we, this is subject of integro-differential equations, very active for a while, where people studied equations, integro-differential diffusion in terms of certain kernels. But the typical assumptions of ellipticity were usually that the kernel was bound above and below by a multiple of the fractional Laplacian, which we don't quite have here. We have a fractional Laplacian somewhere, but this factor can be very large in some directions and very small in some other directions. It still has some sort of non-degeneracy, but we have to understand what kind of non-degeneracy we get for the Boltzmann equation. So what we can get is certain cone of directions in which the kernel is bounded below. So let's see how we get that. Let's suppose that all we know is that the mass is bounded below and above, that the energy is bounded above by this constant E0, and the entropy is bounded above. Then one can prove that the function f is larger than some constant in a set of measure at least mu. This is relatively simple. The mass is bounded below, so there has to be some mass somewhere. The energy is bound above, so the mass cannot be too far away from the origin. So that's how you determine that ball. There is a ball where there is a lot of mass, right? But the entropy is bound above, and that tells you that the mass cannot concentrate too much. And that's how you get a set of positive measures where the function is bounded below, right? Now, once you have a set where the function is bounded below, from any point, there is a lot of directions where you see that set, and in all the perpendicular directions, your kernel is bounded below. So that should be like the picture. There is a set here in a ball where f is bounded below by some constant delta. So if I take any other point v, in any direction that is in a way perpendicular to the directions where you see the set, then there should be a bound below for the kernel, right? So the kernel is not bounded below by a multiple of fractional Laplacian everywhere. It's bounded below in some directions, but those directions make a thick cone at every point, right? The cone may be rotating from point to point, but there is always some thick cone where the kernel is bounded below. And having a thick cone of direction where the kernel is bounded below is some sort of ellipticity of fractional order. It can be understood, like the lower bound for the ellipticity in the typical second order equations. Why do I say that? Because if you have a quadratic form with a kernel, having a thick cone of directions where a kernel is bounded below is enough to conclude the coercivity estimates that this quadratic form is bounded below by the HS norm of f squared. And that's a generic statement about integro-differential diffusions. So this having a thick cone of direction is some form of ellipticity that gives you this non-degeneracy of quadratic forms. So it implies, in a way, the coercivity of the Boltzmann collision operator with respect to the HS norm, which is something that has been proved independently in the Boltzmann literature, but it's also a generic statement about integro-differential kernels. So let me try to explain how one can prove the upper bound. So what I'm going to try to track is the value of this quantity. This quantity is, I have my desired upper bound. I want to prove that f is always less than this little a of t, right? So one way to do is I can look at the positive part of f minus a and integrate it and try to look at this quantity. I would want to say to get that this quantity is identically zero, right? So the way to do it is I'm going to prove that this quantity is monotone decreasing. And because of this choice of, oh, this should be a 2s, by the way. Because of the choice of a of t goes to infinity as t goes to 0. So m is automatically 0 as t goes to 0. So this quantity comes from 0. If we prove that it's monotone decreasing, it's never going to be positive, right? So this is sort of a variational approach to get the maximum principle. So I want to prove that this quantity is monotone decreasing, and that gives me the upper bound, all right? So let's see what will happen. So I want to prove that quantity is monotone decreasing, I just take the derivative, okay? So when I take a derivative, we get this expression. So here I have the collision operator, I have the transport part of the equation, and I have a prime. Yeah, this is what I took the derivative of this expression over here, and then I multiply times the other one because it's squared. Now, and this is the only place that you will see the boundary condition. If you look at the transport term, we can integrate by parts the transport term. We see that the expression that we have is the v dot grad x of this square, and then when we apply the divergence theorem, it becomes a boundary integral. Now, for every one of the boundary conditions that I mentioned in the theorem, this boundary, this expression in the boundary integral is negative, right? If we are in the influx boundary condition, for example, we prescribe the value of f at the points where the velocity is pointing inwards, I would want my upper bound to be above the prescribed values, obviously. So at all the points where v is pointing inwards, this quantity will be 0. And at all the points where v is pointing outwards, then this has a sign, right? So in the influx, we clearly see that this thing that we get here is negative. For the specular reflection, then we will have cancellation, because at v and the reflected value of v, the quantity would coincide and the whole expression would be equal to 0, right? So in all the boundary conditions that I mentioned, this quantity is either 0 or non-positive, okay? So that's what I was saying before when I said, when I do the variational proof of the upper bound, then the boundary conditions are very easy to handle because it only amounts to evaluating that boundary term. So we are left with the other terms, the collision operator and the derivative of my little a, that is my upper bound. You see, I want my little a to go all the way from plus infinity and come down to a finite number, right? So I want to have my a prime to be very negative. And for that, I want to have in order to get a negative value here, my collision operator has to be very negative. So I need to evaluate my collision operator times f minus a and be able to get something negative. So let's see if that happens. So I'm going to split my function f between the bounded part, that is the minimum between f and little a, and whatever is above little a, right? So I'm splitting f between what's below little a and what's above, okay? And so this expression over here is f the same as fr. So I'm splitting the collision operator between the evaluation at fr and evaluation at fp. So here the Boltzmann collision operator is typically a quadratic operator on f, but one can also write it as a bilinear operator. There's probably not only one single choice of how to make it bilinear operator. So this is the way I do it. When I write qf comma g, I'm taking f as the function that defines the kernel, and I'm taking f for the convolution. And I use g as gv prime gv, and also as the one that evaluates in gv. So it's not the symmetric bilinear operator, right? So this qfg is not symmetric in f and g. So that's the splitting. That's the expression I'm using to split f in fr and fb in that expression. Okay. So after you work out the algebra, symmetrize and do the obvious thing, you end up with these 4 terms, right? The first one is sort of the one you would expect when you pair the diffusion part of the Boltzmann collision operator applied to fr with fr. You have the negative of certain quadratic form involving fr square and the kernel case of f, right? The second one comes up when we pair the diffusion operator applied at fb with fr. And it also has a sign. This one is also negative because any point where fr of v is positive, remember that fr is the excess of f over my upper bound, fb is equal to a. So fb is exactly at its maximum. So any point where this is non-zero, fb is at its maximum, and then fb at v prime will be smaller than that. So this thing will be negative at any point where f sub r is non-zero. So this second term is also negative term. The other 2 terms don't have a good sign. They are actually both positive. It's not even that they change sign, right? So that's why these are my good terms, because I want to prove that this whole thing is negative, and that's my bad terms. And the worst term is the second one, because I want to make a prime go all the way from plus infinity to finite, so it has to be a prime has to be very, very negative, right? So when you look at something like this, you should probably believe your first impression should probably be that the first term is going to be the most relevant, right? Because if you think about second order equations, imagine that this was the Landau equation instead of the Boltzmann equation. We had a second order operator. If you have a second order operator, the first line will be like the h1 norm square of f, right? It's like the gradient of f squared, basically. That's the way you have to think about the first line. It's like negative gradient of f squared, but a non-local version of that, a fraction order version of that. And the second term, if you have a second order equation, would just be non-existent, right? That second term is a purely non-local term that doesn't exist in second order equations. Nevertheless, here is going to be the most important term. It's going to be the driving term for my argument. So it's going to be the one term that I'm going to use. And I'm going to, this term is not that I throw it away. You can use it a little bit to compensate for the fact that this is higher order. But I'm not going to use the first term to compensate for the last term. So I'm going to show you now how this term kills the last term. So this is actually the most important term for the argument to work. And let's see how it works. Like I said, in any point where fr is equal to v, maybe I should make a picture. So I can. Is there chalk anywhere? Yeah. So remember what we have. If this is f, and this is a of t, f of r, f sub r is this part in excess over here. Right? And f sub b is whatever is underneath. So at any point where f sub r is positive, f sub b is at its maximum, right? And so wherever this is positive, this is going to be strictly negative. But moreover, we can quantify how negative it is, because f of v prime certainly is going to be less than f of b at v. But we know the mass, we know the integral of f of f sub b, because we have this upper bound on the mass density. We know that the integral of fb is smaller than the integral of f, and it's smaller than this upper bound on the mass. So because the integral of f of b has an upper bound, it cannot be equal to our maximum at everywhere. We can quantify all the distance, let's say that eventually this thing is going to be below. And because we can quantify the integral of this and how many points there can be that v prime is, let's say, larger than half of f of v, then we can get a precise bound on how negative this is. And the bound is going to be of this sort. It's going to be that this thing is less than a constant times a to a power that is larger than 1. Is 1 plus 2s of a t. All right? So basically, that's how negative we quantify that term to be. Okay? So that term is at least that negative times the integral of f of r. So it's a pointwise estimate on that. So basically, when we go back to the formula that we had, and I want to compare this good term with that bad term, I get that this good term has that factor up front as the integral of f of r. So we can make a prime to be as negative as this number.
And this is where you use the moments, right? In the fact that you bound the moments.
The moments?
Yeah.
I'm using only the mass here.
Okay. So
why the moment?
I don't know. I mean, in order to get this bound by the fact that you have a lot of, I mean, the big cone, right? Is based on the fact that you have
the what?
The control of the moment, the mass.
Yeah, but in this one step, I'm using the mass. I use the moment. Well, I use the moment a couple of places. I use the moment to get the BR for the corner on the degeneracy.
Yeah.
But I hear you use the moment just for the balance of the fact that there are some things that I'm not telling you, like the non-degeneracy of my kernel, right, is changing from point to point. So the corner non-degeneracy for my kernel is deteriorating at large velocities, right? So when I'm telling you here that I get that bound, I'm lying a little bit, because there is a weight depending on how large the velocity is. For large velocities, there is going to be some power of v floating around. And to compensate for the deterioration of my cone of non-degeneracy, I use the energy, right? So you have to make sure that your estimates don't get ruined at large velocities. And for that, you have to use the second moment. But I wanted to hide that under the rug. So it's better if you don't ask me. Yeah. Yeah. So anyway, so what I was saying is, if this good term is at least this negative, we can make A prime to be that. And this A prime, this ODE, is an ODE that goes all the way from plus infinity and goes down to finite immediately, right? So I'm not going to tell you how to handle this term because that's sort of like the boring, you have to interpolate or whatever, right? So it's brute force how you deal with this term, right? And to deal with this term, you use also the fact that you bound it by some combination of these two. And let me say that, so I think that there is a driving idea for these proofs that is originated in the study of integro-differential equations. I'm using this expression of the Boltzmann equation in terms of this diffusion kernel, and this idea of getting a precise bound for the quadratic equation by looking at the mass of the function above a level set and looking at the mass of the function below a level set is an idea that I was present in the study of parabolic integro-differential equation, in particular in the paper by Alexis with Chihin, Chan, and Caffarelli, right?
It's kind of that the things are important to the outside. There is the two terms, the two terms inside and the two terms outside. Okay, I think so.
Maybe, right? So anyway, that's another connection, okay? All right, so I don't know what time I started, but maybe I can stop now, all right? So happy birthday.